Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamics lectures. And let us look at, today we want to look at convection in a fluid flowing in a tube. Flow in a tube. Now, if you remember, when we talked about pipes, flowing pipes with annulars and pipes, there are certain concepts which we discussed there. And again, once again, I continue pleading with you and reminding you that go through some of those lectures so that you are up to date with this. So remember that we had, in principle, decided certain things when we were dealing with this flow in pipes. From first principles, the flow in a pipe, in a tube, we say that the heat based on Fourier's law, heat law, we said that Q was equals to minus K 2 pi R minus Y L d theta by dy. That's the expression I got. And this have to do with the radii in that particular tube. And K, as you know, is thermal conductivity. Theta is our temperature there. Now, this particular quantity, if we rearrange this, our very principal equation, which we have derived severally, worked with severally through our lectures, if we rearrange this quantity, this on rearrangement, rearrange this quantity, then we'll have minus Q over K 2 pi L and then we have is equals to R minus Y d theta dy, the relationship. And of course, if we take the derivative of both sides with respect to dy, in fact, we can clear out this and bring it this end. So, on taking the derivative, so that is, we multiply both sides by dy, so we have minus Q K 2 pi L d dy. Let's bring this side. We have that bar over there. So we have 1 over R minus Y is equals to d theta dy equals to 0. So we have simply rearranged these particular quantities. Now, if you look at this expression here, if you want to differentiate it, this is a quotient. This is a quotient. So this quotient, let us call the numerator U and let us call the denominator V. So we will use the identity in differential calculus, that is d of U over V, as being equal to V du minus U dV over V squared. That's the identity which we will use to solve this quotient here. And so if we apply that there, we have called the numerator u, the denominator v. So if we apply that, we have minus q over k 2 pi l. Taking that derivative, we have u is 1, dv is d of r minus y dy minus u. No, we've taken it the other way around. Our v is r minus y, the derivative of 1 dy, that's a constant of course, minus u, that is 1, the derivative of v, that is d r minus y dy, divided by r minus y squared. Remember, the derivative of a constant, it doesn't change, is 0. The derivative of a constant is 0. So all this quantity here will vanish. So what expression are we left with? What expression are we left with? So that's a constant. The derivative of a constant is 0. So that's multiplying with 0, so that all of it will vanish. Then you have 1 times that derivative over that. So we have, and that, remember, is equals to d. Because we have to take the derivative of both sides. We are not written that, so we have to take the derivative because we took the derivative of this side, so we must do that to balance our act. So that is d2 theta over dy squared. I repeat, took the derivative, both sides with respect to y. So we have done that on both sides, and we have used the differential calculus identity on differentiating quotients, and we have used that. We have labeled that as numerator as u, denominator as v, and so we have just applied those quantities there. So we have minus q. So we have minus q over k 2 pi l. We now have the derivative. Remember, that's the derivative. D of minus the derivative of dr dy minus the derivative of dy over divided by r minus y squared. And so dr dy is 0 because there is no y there. That's again a constant. That is also 0. So this whole quantity is 0. So minus minus is plus. So we are left with minus, and that of course is d2 theta dy squared. So we are left with minus q over k 2 pi l. And then we have dy by dy. This is unity. This is unity. That's 1. So we have minus q over k 2 pi l. We have 1. We have 1 there over r minus y squared is equals to d2 theta dy squared. Very straightforward. Pretty straightforward in this particular case. And so if we continue further with the rearrangement, is q over 2 pi kl r minus y squared is equals to d2 theta dy squared. And so if we substitute that q, which we started off in the Fourier's heat law, then we have minus k 2 pi to r minus y l theta over dy divided by 2 pi KL r minus y squared is equals to d2 theta dy squared. Very straightforward. You just move systematically. So we have just rearranged the quantities. We have taken the changes in the system itself. Now, what do we get? What do we get for our solutions here now? Let us look at it now. What do we have for our solution? So we have the r minus y will cancel with the r minus y squared, leaving r minus y. K 2 pi will cancel with the 2 pi k. L will cancel. So we are left with minus. We'll have minus. We have minus. So this will cancel. We have minus 1 over 2 pi. 2 pi are cancelled. So we are left with r minus y d theta dy is equals to d2 theta dy squared. dy squared. And so when y is equals to 0, then we'll have d2 theta dy squared is simply equal to minus 1 over r d theta dy. Now, we talked of parabolic solutions. Here we are talking of a laminar flow in a tube. Let's just craft that. Let's just craft our laminar flow in a tube. Just to remind ourselves. Remember, we have the area. This is an inviscid or irrotation. We have inviscid or irrotational fluid. Like we have said earlier in our lectures, the elements in that fluid do not rotate about their center of mass. Then, of course, we are developing the boundaries. We are developing the velocity boundary layer. So we are developing it. And as we progressively move on, so let us say that this is the region where the laminar flow is fully developed. This is the velocity boundary developing. And of course, this is the entrance length. And so the flow is developing. And we say that this velocity boundary layer, let us put that's the axis. That's the axis. This velocity boundary layer. That is velocity boundary layer. That's the axis of flow. That's the velocity boundary layer. We are developing. The velocity profile is developing. And at the tail end there, we have the laminar flow. And remember, we talked about the significance of Reynolds numbers. And as we move on, there could be some velocity gradients within the fluid that can generate turbulence. But we don't want to go into that. So that's just to remind ourselves. That was just to remind ourselves that you remember that pattern, that schematic which we had that day. So we are saying that 1 over r minus 1 over r d theta dy is equals to d2 theta dy squared. So because we said that this velocity profile is best described by a parabolic equation, so velocity profile is described by a parabolic equation where theta is equals to ay plus by squared plus cy cubed. And so, if you take the first derivative, d theta by dy, here we'll have a, remember, taking derivatives, x of n, the derivative of x of n is n to x minus 1. So that's the identity we are using there. So day by dy is a plus 2by, that is 2by, that is by, plus 3 cy squared. If you take the second derivative, d2 theta by dy squared, that's the second derivative, is just a derivative with respect to y of d theta dy. So, of course, that has no y, so it will be 0 plus 2b plus 6 cy. And when y is equals to 0, then that term will vanish, so that d2 theta dy squared will be 2b. So we have these two very important quantities. Those are very important quantities which we have for here. For d theta we had that. We have that again here when y. So for d theta by dy, when y is equals to 0, will be given by, when y is equals to 0, it will be given by a, because that will be 0, that will be 0. So we have for d2 theta squared, dy squared is 2b, for d theta dy, y0 is a. These are very important quantities, because these are quantities which, when you combine with the boundary values, then you can actually get the actual parabolic equation. Now, we have these particular quantities. So we have, this is d2 theta. So d theta, so from that we can say that d theta, we can see that d theta there, d theta dy is equals to r d2 theta. So d theta dy, d theta dy, you can see is minus r d2 theta dy squared. And in the same way, we have for d theta, now if you put in our values, d theta, d2 theta dy squared is equals to minus 1 over r d theta dy. And what is d theta dy? Is a, so that is minus a over r. Minus a over r. And we also know that for d2 theta squared, it's actually 2b. It's actually 2b. And again, so that means d2 theta dy squared is equals to minus a over r, but that is also equal to 2b. So that we have a is equals to minus 2b r. So we have these particular expressions here now. We have these particular expressions here. And so you will find that for the parabolic equation, for this system, when you solve for these a's, b's, and the other values based on the boundary values, so using the boundary value, the value, and the values for a, the values for the constants, then you will find that the parabolic expression is (6/3) y over r plus 6 over 5, sorry, 3 over 5 y over r squared plus 4 over 5 y over r cubed. So these are the values, these are constants. You can get them once you use the appropriate boundary values and the values for the constants, just like we are solving these particular values here. We can solve b further, we can solve for a further and get those particular values. So that in a nutshell, Q, our equation, Q, remember Q was minus 2, my case here, minus K d theta by dt, theta by dt, forgetting 2 pi K, remember, R minus Y, that's what we had initially, the theta by dt. This is what we had initially for our values. And now we know, we have gotten Q. We now know that our Q, this Q here, which is minus 2 pi K R minus Y, and we have gotten values, we have gotten our values. We know what the theta by the theta by dy, not t. We know what the theta by dy is. It is A. We have that particular one. So we have here Q being equal to minus H into T. This surface as T wall. And remember that was the convective transfer coefficient. Convective transfer coefficient. Now, we can actually get a value here. We can actually get a value here if we truncate this quantity. The first term, let us truncate it. The first term. So if we truncate it to the first term, so that we get some actual value, truncate to the first term, then we can say that theta over theta r, if we truncate to the first term, is equal to 6 y r. So that theta is equals to 6 5 y r. So that d theta by dy, d theta by dy is equals to 6 over 5 r. 6 over 5 r. So we can plug that in here. Let us just leave this as our constant K, the general Fourier heat law. General Fourier heat law, let's just leave it as Q is equal to minus K d theta dy. Of course, let's just leave that surface, let's just leave that as area to make our life easy so that you don't have to worry about that. So just leave it in a simplified form. That's the area over the flow and so forth. So that what do we have now? That is equals to minus H Ts minus Tw. And so we put in the quantity here for d theta by dy. We just work with the parabolic equation. I've said we have truncated it to the first term. In other words, we have ignored the higher terms. So just left it as this ratio, theta over theta r is 6 over 5 y r. And we have just taken that particular derivative, so that with respect to y, so it's just 6 over 5 r And so we can put that expression here in the Q, therefore, is equals to minus K A 6/5R is equals to minus H to T S minus T W. So basically, this equation here will give you the rate of heat transfer per unit area of the wall. This is the rate. Give you the rate of heat transferred per unit area of the wall. Very simple. So what have we done? Just from first principles, where we have worked with tubes, and we have worked with pipes. We have always made the assumption we know what this area is, that this area is 2 pi into r minus y, and we have worked with it in the same way. And so we have just used the parabolic equation and coupled it with the convective equation. And so we remember this is the convective heat transfer, coefficient. Don't forget that. We have derived this in one of our earlier lectures, so I continue encouraging you to follow up with some of those lectures so that we are all together, we move at the same pace. And so when we have just worked with these quantities, we are able to get this relationship which gives us the rate of heat flow, that's the rate of heat transferred by unit area of the wall. And remember, you have seen we have gotten the values of those constants. So using that coupled with the boundary values, you can actually compute exactly what those constants are. So let us stop at this particular point. So we've just looked at this convective laminar flow in a tube, and we have seen that we can actually come up with the expression for heat transferred per unit area of the wall. And so we'll stop at that point. We continue with our lectures.